Hi, folks. This week we continue our exploration of propositional logic, and I'd just like to say that this is probably some of the most unfamiliar looking material, as you know from last week's assignments, reading and the homework assignment. But it's a little bit like math, and it actually connects to our natural ways of reasoning. So it may look scary, but it is abstract in that it is symbolizing things rather than stating things like we've been dealing with in the course up to now. But it is understandable. It makes sense. It's not extremely strange in and of itself. In fact, if you give it a chance, you may very well find that it is actually fun to do this stuff. So I'm going to take my time with this video. It may be kind of a long one like last week's, maybe even longer, but I want to do what I can to help you understand this material. Understand that this is a supplement to what's in the book. It's not a replacement. And there's going to be a couple of things that may be slightly different from in the book, but it's all meant to help you succeed in doing the assignments better, in being able to do well on the exam on the material. That is the quiz, sorry. And ultimately, I think if you give it a chance, like I say, you might find that it's actually kind of fun. Okay, I'm sure you're probably sighing. Many of you are sighing right now, but give it a chance if you would. Give me a chance. Okay, so I'm going to share the screen with you. First of all, let's go over some of the first part, just to reorient ourselves to what we're talking about here in propositional logic. Propositional logic is based on natural forms of reasoning. That means that you will be able to recognize intuitively that these basic argument forms actually make sense. They're valid, and validity is something that plays a huge part in doing, actually the key role in doing this week's material. So we'll need to let go for a while of many common uses of the word valid. That is, we don't want to think of valid as being true. Truth is a different thing. It's a value that we're going to talk about also. That's also key. But the term validity or valid means something very specific. And so it's best to not try to find, I think, synonyms or different ways of saying some of these definitions, but really try to focus in on the way that they are stated in their definitions, because it's really easy to go astray with, oh, well, valid is just saying something is true, or finding other ways of saying things than that they are stated. Okay, so what I've done here is I've taken the document from last week, the demonstration from last week, and I've put a little text in the beginning. So I'm calling it version 2 and putting it under this week as well. There'll be 3 documents this week. One will be the demonstration from last week, slightly revised with the chapter summary at the beginning. Then there's the demonstration that I used today on the second part of the chapter 6. I'm calling it part 2. It doesn't say part 1 and part 2 in the book, but I'm using those terms. I should say that the part 1, what I'm calling part 1, the document, this document for that contains part of the summary, mostly the stuff that relates to this part 1 stuff from last week, some of which relates to this week. So anyway, it'll make sense once you start reading it. Okay, so just to kind of summarize here, I'm just going to read a little bit and maybe comment on it, because the way that it's worded is, I think, very helpful, and that way we won't go astray, as I say. In propositional logic, we use symbols to stand for the relationships between statements. Okay, remember, statements are things that can be true or false, and that's the only possibilities in the world of logic. You have two truth values, true and false. So if I make a statement, the table is brown. John went to Baltimore. Detroit is west of Bangor, Maine, or something like that. Those are statements, either true or false. Now, fictional statements can be true or false too within the world of the fiction. So Sherlock Holmes lived at 220 or 226, I forget, but whatever it is, 220, let's say. Sherlock Holmes lived at 220 Baker Street. That's a statement also, and has a truth value. We say it has a truth value, and that means that it is either true or false. So it has the truth value true or the truth value false. Now that statement about Sherlock Holmes, of course, is only gets its truth value based on the world of the fiction. So that's how statements work. They're the meaning of declarative sentences. So we're going to be talking about, or continue our discussion about argument forms here. So again, we use symbols to stand for the relationships between statements to indicate the form of an argument. Okay, that means not necessarily the content, but the form, because different content can have the same form. These relationships are made possible by logical connectives such as conjunction, which in English means and, disjunction, or negation, not, and the conditional, if something, then. So if one statement, then another statement. Connectives are used in compound statements, and I marked this part out. So I got some of this text from the book here, and it says at least two simple statements. There's a couple of typos in the book. I apologize for that. If you see something in the chapter that looks very strange, don't panic. It may be a typo. It may not be you. It may be a typo. There's 3 or 4 of them. I apologize for that. I didn't write the book, but I apologize for that. And I think it's misleading to say that connectives are used only with 2 simple statements, or that seems to be implied here, because the negation operator, the not, is sometimes called a monadic operator, and is thought of as a connective, and that's just one statement. So a statement is a sentence that can be either true or false, right? Truth value true or false. Those are the only possibilities. To indicate the possible truth values of statements and arguments, we can construct truth tables, a graphic way of displaying all the truth value possibilities. Okay. A conjunction is false if at least one of its statement components, right, one of the conjuncts is false. And I'm just going to come down here real quick to the, remember, a conjunction operator is an ampersand, or sometimes it's the inverted wedge. Sometimes it's a dot. In different textbooks and different places, I'm going to show you a handy rule sheet where the operators are slightly different, but they're reminiscent usually of what it is in this book. So shouldn't be too hard there. Now you remember the example of conjunction there. I just want to show you the truth table. So the only time, remember a truth table, is you have the 2 atomic sentences, that is the single statements. You have the 2 single statements. You set those up first, P then Q, because there's only 2 statements, and then the conjunction itself, P and Q. This is the operator, and the operator is where the truth values go under. That is, the truth values for this whole thing go under the operator. So that's to distinguish these from any values that might be under these others, okay, under P or Q. So when P is true, this is saying when P is true and Q is true, then P and Q is true. When P is true and Q is false, P and Q is false. Now, sometimes I should say it might be good to just kind of start to memorize some of this stuff, at least until the connections become clear, because sometimes if we kind of bring along, well, what is this saying about, you know, how do you know that something is true or not, or so-and-so, it will start to sink in while we're doing this, even though the author says it pretty clearly. It took me a long time to sort of reconcile everyday speech and everyday reasoning with how it's symbolized. So if you're in the same boat, don't worry. Just try to go along with the methods, the techniques here, and it'll start to sink in over time, I think. So when P is false, Q is true, then the conjunction is false, right? So that's obvious. If P is one statement and Q is another, and we want to assert the truth of both of them. If one of them is false, then the both of them are false. If I say I'm going to the store, and 2 and 2 is 5. Okay. Now my first statement is true, but the conjunction of both of them is false, right? Even though I am going to the store, or let's say that's true. I'm going to the store and 2 and 2 is false. That's false, right? Now if I said I'm going to the store or 2 and 2 is 5, well, that would be a true. That would be the disjunction. So you'll notice that in the disjunction, we're using the inclusive sense. So if either one or both are true, then the disjunction itself is true. The only time a disjunction is false, right? This is either one thing or another. The only time it's false as a disjunction is when both of the statements are false. Let that sink in a second. In a conjunction, on the other hand, it's only when both of them are true that the conjunction is true. If either one or both of the conjuncts, right, the statements that make up the conjunction, if either one or both are false, then the conjunction is false, okay? So that's important to remember. Now let me come down here because we're going to be dealing with this too. Let's look at the negation. Now negation truth table. There's only one statement, okay? So we're calling that P, and that can either be true or false. So underneath the P, the guide, what the book calls the guide column, just tells you all the possibilities of P. There's only 2, true and false. But now notice, not P, remember that's the negation operator, not P is false when P is true, and it's true when P is false, right? So it flips it. Now again, what you can do is put underneath the P, put what this is over here. Now when I make truth tables, when I write them out, and I actually enjoy writing truth tables, that's how strange I am, I guess, is I just write all this out. So that way I can see it very clearly. So P is true, and so I just write, again, I just write the same thing, true, under P. So then it's obvious in a negation, it's false when P is true. So this is just a sort of a even more clear representation of doing it. So just kind of letting you know, that's one of the reasons why it makes sense to put the true and false underneath the operators. So in a conditional is a little stranger, okay? In a conditional, I know I went over this last week, but I just want to go over it again, just because what comes next is really based on this. So the conditional means, what you read this as is if P, then Q. Okay. So if one statement, P, then another statement, Q. So what's the logical status of that? Right? How do the truth values change depending on the truth values of the statements? So the individual statements are all given here, all the possibilities. And you start on the left side, and how you set up a truth table is on the left side. You just do half T's and half F's, okay? And then the next one in, you half the T's and half the F's and do them alternating like that. And that's how you make sure and get all of the possibilities in there. So for when you only have 2, it's not hard. When you get 3, 4, and 5, that's when it's good to remember this. So TT, FF, and then TF, TF. These are all the possibilities, all the truth values for P and Q. And what you find here is the only time that a conditional is false is when it's called the antecedent is true and the consequent is false. That's the only time the conditional is false. All other times we're calling it true. And this was a weird one. You see the video that I did last week. I talked rather at length about this. It just has to do with it's true if I go to the party, John goes to the party. If that all happens and that's true, then the conditional is true. If I don't go to the party, John could go to the party. It's undetermined, right? We can't say that it's false, so we're calling it true. That's what we do in logic. And if it's false that I go to the party and it's false that John goes to the party, then the conditional didn't obtain. You didn't see the results of me going to the party and John going to the party. So that's called true too. The only time is when I go to the party and John does not go to the party, right? Then the whole conditional, if I go to the party, then John goes to the party, is false. Then that's false for the whole conditional. Okay. So I just wanted to go over those in a little bit of detail there. And so that's what this is all summarizing. Now, we use truth tables to determine the validity of an argument based on the fact that it's impossible, remember this, it's impossible for a valid argument to have true premises and a false conclusion. Remember how we define validity, right? Deductive validity. We've left inductive arguments behind for this chapter. We're just talking about deduction, and deductive arguments. So deductive validity is valid only when the truth of the premises necessitate the truth of the conclusion. So an argument is invalid if you have true premises and a false conclusion. Okay. A basic truth table consists of 2 or more columns, guide columns, listing all the truth value possibilities, followed by a column for each premise and the conclusion. So we're going to extend these truth tables out a little longer, a little bigger. You've seen that in the chapter. I'm sure you've read it. We can add other columns to help us determine the truth values of the components. Okay. You can check the validity of arguments not only with truth tables, but also with the short method. Okay. That's actually an interesting way. You have to just understand the concept of how it works. All you really need to understand is that we want to try to prove in the short method that that we can force a row of a truth table to have 2 true premises and a false conclusion. So let me say that again. In a full truth table, what we're going to be looking for is the premises to be true and the conclusion false on some row or other. What we do in a short method is we try to force that row. And if we can't force it, then the argument is valid. If we can force true premises and a false conclusion, then we've proven that the argument is invalid. In this procedure, we try to discover if there's any way to make the conclusion false and the premises true by assigning various truth values. Okay? So now we'll go over to the second part. Now, finally, the method of proof is a way to confirm the validity of an argument by deducing its conclusion from its premises using simple argument forms. Okay? Most valid complex arguments consist of several of these valid sub-arguments, most of which you may already know. Remember, what they're talking about here is modus ponens and modus tollens. Funny names, I know, but it's Latin, and that's what they're called. So philosophy, logic has its jargon, just like psychology and physics and everything else. Determining the validity of the larger argument then is a matter of moving step by step from premises to conclusion, identifying the valid component arguments along the way. This will become clearer as we go on. The method of proof uses 9 rules of inference and 9 rules of replacement. And you'll have a chart, and I'll show you the chart right here. There's one in the book too, slightly different. But this all looks weird probably to you now. So be sure and read the book. And just like I say, there's a couple of typos. And actually, I think I can tell you what those typos are. Let me mention them now. That I found on page 211, the big argument truth table. It's pretty confusing. So don't worry too much about that table. I think it sort of makes it difficult. Let's see, where else did I find something here? Was there something else? Maybe that was it. Maybe I was just so upset by that I just magnified it in my mind as being more. Well, okay, I guess that's the only blatant one that I saw in this part of the chapter. Okay, so let's look at some of these exercises from this week. Now, like last week, I blacked these out just so as I'm showing them to you, we can think about them, sort of think them through here. Okay, so what we're looking at in 6.8, construct a truth table for each of the following arguments and indicate whether the argument is valid or invalid. Okay, so you remember how we set up the truth table before? We put the individual statements first, P and Q. Okay, I'm sorry, I'm getting ahead of myself. So here's the argument right here. So we have if P, then Q. So that's how we read that. This is a conditional, you remember. If P, then Q. So that's line 1. We should really be using lines here, line numbers, I'm sorry. So premise 1 is if P, then Q. Premise 2 is P. So we're assuming now that these are both true. And if they are both true, then the argument is claiming, now these 3 little dots here mean therefore. That's all it means. Therefore Q. Okay, so that's what we're reading here. That's what we're seeing. If P, then Q. So if it's true that P, then Q, and P is true, then Q is true. Now you can see right off that this is a valid argument because, for one thing, it just makes sense. I mean, this is a modus ponens right here. That is, if I go to the party, then John goes to the party, and then if it's true that I go to the party, well, if it was the first one was true and the second one's true, then you'll see John at the party, or at least he'll be there. He may be hiding, but he's there. It's valid because if 1 and 2 are true, then this has to follow. It absolutely has to follow. This is an argument form. It's called a valid argument form. So you could put anything in the world in for P. You could put anything in the world in for Q. This is going to be a valid argument form. Remember, valid doesn't mean true. So you could put, if space aliens are examining me awkwardly, then I will become one of them. okay? And space aliens are examining me awkwardly. Oh, that's a weird sentence, I know, but it's a statement. It's a weird statement. Okay, I apologize, but I'm not going to go back and start a new video just because I said something a little weird. I'm going to keep going, push forward. If they're examining me, and if they examine me, then I'll become one of them, and they're examining me, therefore I will become one of them. That's just follows, okay? So what we're doing here is we have a column for P, for the examination, the awkward examination. We have Q for my following them, and then we have the argument. This part is the argument. Now, when I'm writing these up, I'll like writing them by hand. I'll put like two lines here just to sort of demarcate the components from the actual argument. But here's the argument. It's if P then Q, P then Q. So if we're looking for what we're looking for here is we're going to put all the possibilities of P and Q together in this argument and see if we can find one row where this statement is true and this statement is true and this statement is false. Remember, if you have true premises but a false conclusion, then you have an invalid argument. Okay, so remember how we set this up. We put all the, we put 2 T's and 2 F's for P, and TF. Well, actually, what would that be? So there's got to be 4 possibilities. Actually, how many possibilities? There's actually a way to write this. It's 2 to the n. Well, I'm not going to put it, but if you put a little superscript. Actually, can I do that on font? Was there a superscript? I think there was a superscript. Yeah. Yeah, look at that. Oh, no, n. There we go. All right. So 2 to the n, that's how many rows. This tells us how many rows there's going to be. So the n is just means how many equals kind of component statements, okay, in the argument as a whole. So in this one there's 2, so there should be 2 to the second. So 2 times 2 is 4. So at least where I come from. But I don't know. We're weird in other ways where I come from, so maybe it's different somewhere else. But 2 and 2 is 4, as far as I know. So there should be 4 possibilities. So I'm going to open this up now. Let's see here. Okay, and so there's 4 possibilities. So the first column gets 2 T's and 2 F's. The next column breaks these up. So it does half as many. I don't know how to say this. It alternates half of what this says. So 2 T's and 2 F's for P. Q gets TF, TF. Now, you might be asking, could I have put Q where P is and P where Q is? Yes, you could, and it wouldn't matter, right? It wouldn't matter, because you would still, if you set it up this way and if you put Q over here, you could actually, the convention is to always on the left put half and half, T's and F's, and then half as many of each alternating in the next one, and then half as many as that alternating if there's a third one, and then half as many as that alternating as the fourth one, and then so on. But you still have to set it up this way with TT, FF, TF, TF. You can even put Q over here and have TF, TF, and then in this one have TT, FF. You'd still get the same combinations, okay? I'm just going into this to let you know that there's flexibility here in certain areas. But what you want to do is you want to generate all the possible truth values, of which there are only 2, true and false, of the component sentences. Now remember, the let's see, this should be over just a little bit, remember, because we're going to put each of these truth values underneath Now these are the truth values for, I don't know, how am I getting that? I'll check for that, go away. So under the conditional is where I'm going to put these truth values, because now we are into the argument. So the conditional is what we're looking for the truth values for. So what this is saying is that when P is true and Q is true, then if P, then Q is true, right? Remember our truth table, and you can look at the truth tables to help you with this until you sort of memorize them, which is not hard to memorize them, but you know, it could help. So help you go faster anyway. So now remember that the only time a conditional is false is when you have an antecedent that's true, like you do here, P. Q is false, so that makes the conditional false. All these other possibilities, false, true, false, false, gives you a true conditional. So now these are all the possibilities for this conditional. Remember, P and Q could stand for anything as long as it was a statement on the left and a statement on the right. If this statement, then that one. You could even have compound statements. You could have complex statements as P. P could be 30 statements, and then Q could be 50 statements, say connected by conjunctions or something like that. You would still have this form, you'd still have these truth values for the conditional itself. Okay, so now under P, this is the second premise, remember? So, you know, number one premise is that one. Number two premise is just asserting P. So these truth values are going to be the same as they are over here, because these are all the possibilities for P. Now Q is going to have all the possibilities of Q here, right? Because this is just, these are the possibilities of P and Q. So this is what Q is here. Now, what we're going to look for, is there any row where the premises, that's these two guys, are true, but the conclusion is false? Okay, so not here, because these two are true, but Q is true. Okay, not here, because this one is false for the first premise and true for the second. So it's false for the conclusion. You may just have to go along with this. I know this is probably where you start thinking, oh, but you know, how does this relate to the actual statements? And how, you know, try to just leave that behind for a minute and just remember this. True, false, right? That's not going to be a row where you have true premises and false conclusions, and true, false again. You know, for the premises, not going to have. So what this means, strange as it may seem, that there is no possibility for the premises to be true and yet the conclusion false. Therefore, this is a valid argument. Okay. Okay, let's do a little bit bigger one here. So number 7. Now these are the ones that are in the back of the book, except I'm going through and explaining them a little bit more. If you have trouble with the ones that you're working on, ask about them, but I want you to try them on your own first and not just look for the answers. I want you to try these, because there's a mechanism here. You know how when you first got shown how to do long division, you know, the method of doing it, it looked strange at first, but once you started to use the process, it started to make sense. So here we have a little bit more complex argument. We have a conditional, we have a conjunction, right? This conjunction, this is the main operator here, because on the left we have the negation of Q, on the right we have R, and then the therefore R. So premise 1, if P then Q. Premise 2, not Q and R. That's how you might read it, or it's not the case that Q and R, but most folks just say not Q, so they know what they mean, because that's the not sign or negation. It's more clearly, it's not the case that, and then if Q is unicorns are real, you know, then this means it's not the case that unicorns are real. But just not Q is sometimes just how we say it, therefore R. So we want to know if this is a valid argument. Now this one you might be able to tell is a valid argument. I really should if you just really thought about it. Well, it makes sense. If P then Q and then P, then certainly Q follows. But so does R follow from these premises? Well, we're doing a truth table. So once again, we have, we get P, Q, and R, right? Those are the three, the three component statements. Now remember, three component statements. So the one down here is 2 to the third, because component statements is the exponent. So 2 to the third is going to give us what? 2 times 2 times 2. 8. Okay, I'll edit that out later. 8 lines, okay? 8 different lines. So you'll have alternating T's and F's for P. You'll have half as many alternating for Q, and then half for Q, half of that for R. And then these are the premises right here. The premises always come first, and then the conclusion is R. So it just mirrors this. We got our, oh wait, what we got? Oh, okay, this is a little bit confusing. They're throwing in not Q to sort of, that's probably what they're doing in 211. Yeah, so he's doing this thing where he's putting another column to make it easier, where he's putting what not Q is. Okay, so these are our premises, right? Obviously, because if P then Q, the conjunction of not Q and R, those are the premises, and R is the conclusion, as you can see from over here. So we're going to just carry over these truth values over to these premises and this conclusion, and see what if we can find a row that where there are where there are true premises for these two guys, right? And it's going to fall under the conditional here and under the ampersand here, and yet a false for the conclusion. Okay, so let me open this up and see what we got. Okay, all right. So I didn't want to have all this visible and confusing and too much data going in while I was explaining that first part. So these are just the numbering the rows, okay, just to kind of keep it clear. This one is just for convenience. These here, these are the columns that are the basic statements. So you can see here alternating 4 T's and 4 F's because there's 8, right? Then half as many alternating 2 T's and 2 F's, 2 T's and 2 T's, 2 F's, 2 T's. No, that's done. That's got to be a, this has to be a, that's got to be F. See, sometimes, I got this from the book, so sometimes they make a mistake. But that's got to be that way. That's got to be an F. Okay, so under R, you have TF, 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 you see? So these are all of the possibilities there for the component statements. So this is good. So we'll check and make sure that this row actually makes sense. I'm going to highlight this in yellow. And have to remember to go back and change it in the one that I put up on the site. So if somebody sees that I didn't, please remind me. I would appreciate that. Okay, so not Q is just out of convenience. So wherever you see Q is true here, you'll see not Q is false. And then when you see Q is false, you see not Q is true. That's just to sort of help us out there. But these are the premises. And actually these, like I said, these should all be under the operator, right? Not the not under the statements themselves. Okay, and then this should be under the ampersand. Okay, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, all right. Okay, so let's see here. So remember, okay, so what we're ultimately looking for is a T under this one, a T under this one, and an F under this one, okay, in one of the rows. So let's see. When P is true, Q is true, and R is true, okay? If P, then Q, this thing, I wish that thing would just go away. Can you just go away? No. Okay. Let me do this. Oh, nope, didn't want to do that. Hello. Okay, what I want to do was annotate. Let's see what this does. Okay, there we go. It's a bolt fire. When these three are true, then if P, then Q is true, and not Q and R is false. Okay, now why is that? Well, when Q is true, see right there, not Q is false, right? So we could put a false right under this one here if we wanted to. And that means what we have in this conjunction is false and true, and that's always false. You can go and look at the truth table and remind yourself of that. So premise 1 is true, premise 2 is false on this row under these possible truth values. So this is not going to help us in determining whether the argument is valid or not. Because what we're looking for is a row where both of the premises are true and the conclusion is false. That would tell us if it was invalid. Okay, so you see what's going on here. Now, in this one, premise 1 is true, premise 2 is false, so that doesn't help us. False, true, right, doesn't help. False, false, doesn't help. True, false, doesn't help. True, false, doesn't help. True, true, doesn't help. Let's see, now this is a 1. Let's make sure that, this, see, how do I get out of this? I forgot. How do I get out of this? How do I? Oh, look at that. Oh, okay. Well, let me do this. Well, so how do I? Oh, look at that. Okay. I'm sorry. I'm getting off here. Oh, clear. That must be it. Okay. Clear. Clear. I drawing. Oh, that was that. So undo. No, I want to. Okay, here we go. Okay, so when Q is false, let's see here. Wait a minute. See, okay, so let's do this. So this is, I'm making this under Q, and P is false on this row. Okay, that's right. Okay. So you see what I'm trying to do here. When P is false and Q is false, then for the conditional, then that's still true, okay? Oh, but wait a minute. Oh, that's right. So when Q is false, then not Q is true. So under this one is true, this possibility. And then R, we can see over here, the possibility on this row is that R is true. That's supposed to be right under R. Okay, what's going on here? Oh, well. Yeah, okay, so so then it is, so that is true, okay? Oh, wait, what happened over here? So R is true, so this is true. So yes, that doesn't really help. So this is not a row where you have true premises and a false conclusion. Similarly, true premises, premise 1 true, premise 2 false, false conclusion. Again, not a row with true premises, false conclusion. So on no row is there a true premises and false conclusions, so this should be valid. And if it's not, I will, yes, very good. So that's valid. See, it's not invalid because you don't have any row where you have true premises and false conclusions. Okay, I oversay this because I want this to sort of just like stick in your brain like a, you know, like a bad song, like, or a good song. Yeah, I should say a good song. That way, that's the way you'll think of it instead of trying to, in this case, put it in your own words, which can be misleading, as I was saying earlier. Okay, in this one, we have 1, 2, 3 different elements. And so when we're putting this argument together, P, Q, and R, then it gives us not P as a sort of convenience. So the actual argument starts, you can tell where the argument starts because the first premise is if P, then Q. So that's this one. So here are our premises. Here's our conclusion, not P. And so we're going to look for any row where we have true premises but a false conclusion. Okay, so we're going to ignore that these all should be right under this, and these all should be right under the wedge here. Okay, these all are right because they're right under the negation. Okay, so is there a row where we have true premises and a false conclusion? Any row? I don't see one. True, true, true. True, false, true. True, false, true. No. So it looks like that's valid. So you see how quickly we're able to tell by looking at a truth table or constructing a truth table to find out if it's valid or not. Oh, 6.9. So 6.9, I hope that's clear for what you're being asked to do, set up truth tables. You can use these, there's one reason I put these on the core site is that if you have Word or you can get an RTF, which you should be able to turn even Mac documents into RTFs, and you should be able to use this kind of format, copy, and then adjust it for whatever you have, whatever the problem is in the book. So maybe things can go a little faster. Just make sure, and you have to go through and make sure that every single one of these is in the right place. Now, it's not, it's attention to detail that we're doing in this this week, but there is a there. So there's some methods to help make it go a little faster, okay, including how I was talking about truth and false in that sort of guide, in those guide columns. So now we're on 6.9. 6.9, for each of the following arguments translated into syllables, construct a truth table and determine its validity. Okay, so this is just putting these into a truth table. Jake is a plumber, or Jake is the carpenter. Okay, so that's obviously a disjunction. Jake is not the carpenter, therefore Jake is the plumber. Okay, so this is a truth table. You see we have, once again, the premises here, and then the conclusion here after the two statements, the two main statements. So let's open that up. TTFF, TFTF, and then we have P or C, not C and P. So we look and see if there's any row where we have true premises and a false conclusion. I'm not sure what this is, what that middle one is. P, okay. Remember that the disjunction is only false when both sides are false. So you see that, and again, these should be right under this wedge there. So it's only false when both of them are false. So at least from the looks at this, it doesn't look like it's there's any invalid row. So I'm going to say valid. Okay. All right. So I'm going along a little bit faster here. It's number 11. You're going to have to watch this video, and I hope you've been watching this video and short segments throughout your day, hopefully. Number 11, unless both Mary goes and Henry goes, the party will be a disaster, right? So you have Mary goes and Henry goes. Those are the individual statements. So whenever it says a negative or negation, in English, you want to make your simple statements positive so that you can use the negation. Now, this is tricky because remember unless. Let's see, how did that unless go? What was that? Back on unless. That was tricky. 202. I will walk the dog unless it's raining. If it's not raining, I will walk the dog. So you let's see here. So that's a conditional where you negate the consequent. So let's see. What comes after unless is negated and moved to the antecedent. Okay, and then the other one's made it consequent. So here on number 11, unless both Mary goes and Henry goes, the party will be a disaster. Now notice this could say the party will be a disaster unless both Mary and Henry go. It would still be this form because the unless always comes before the negation. The unless means a negation of the antecedent. So whatever comes after unless has to be moved to the antecedent of a conditional. Okay? So the party will be a disaster because that's what that one means. And then therefore both Mary and Henry will not go. Right? So since you have not, so you think, well, both of them will go? No. So it's not the case that both will go. So here you have the elements, M, H, and P. You have a little helpful column there that he gives us. And then you have the actual premises. Premise 1 is here. Premise 2 is with P. And then the conclusion is this one over here. Okay. So let's see this. So we build it. And it's just mechanical. So you build this thing by putting one of them, probably the first one. It doesn't really matter. You'll still get all the same possibilities, even if you had H and P mixed up. Half T's and half F's on the first column, half of that alternating on the second one, 2 T's, 2 F's, 2 E's, 2 F's. This time they got it right. TF, 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 TF. TF, and then this little helpful column here for not M and H, which is just there so that we can, to kind of help us know what not M and H is here. So like, for instance, for the conditional here, we don't have to fill out all of these things, like put M under here and H under here, and then, let me get that thing again. If I was writing this out, I would put M again. I put this whole column. I just put it under the M here. And I say I'm writing really small at this point when I'm writing, but so this is a little bit helpful. So when not M and H is false and P is true, then the conditional is true. So you see what they're doing here. So when not M and H is false and P is false, then the conditional is true. And you can continue that on down. When not M and H is true, but P is true, then you have a conditional true. And remember, this is only false when the antecedent is true and the consequent is false. Okay? So are there any rows? Remember, these are the, let's see, I have a thing here. Where's that draw? Okay. So these are the premises right here. Is there any row here where we have true premises and a false conclusion? Oh my gosh, does it look like this row here? True premises, false conclusion. All right. And actually, does this one have any more? Nope. So there's one that way. But that's all it takes, one counterexample. If you have one counterexample to a supposedly valid argument, so that you can give the counterexample as true premises, where your premises are true, but your conclusion is false, then you have proven that the argument is invalid. So that's why this one is invalid. Okay. Boy, it's a long one. I know. 6.1, 6.10 is going to use the short method. Short method, a lot of fun. Check the validity of the arguments in 6.8. Let's see, use the short method. Okay. And then I think, yeah. You know what? I'm just gonna keep going. What the heck? So we start with a simple one, A and B, and then A. So we're just gonna put the premise and the conclusion. So remember, A and B needs to be true, and A needs to be false, right? So really, the conjunction has to be true. So we're forcing an invalid row, right? We're looking for a row just like the one. Let's see, what an eraser. How does this work? Okay. So we're looking for a row where we're trying to force a row where we have this conjunction is true and the conclusion as false. But notice here that if the conclusion is false, then this conjunction is going to be, the conjunction is going to be false, right? So therefore, there's no way you can have a row with true premises and a false conclusion. And so this has to be valid. Okay. This one here, P or Q, P, therefore not Q. Okay. Now remember the, let's see if I can do this. All right. So, premise one, this has to be true. Why does it have to be true? Because we're trying to force an invalid row, an invalid argument row. And that's where the premises would be true and yet the conclusion would be false. Okay? And then the idea here is that we can force this because putting these values in for the statements themselves and the compound statements will tell us something about the truth values of the individual components. So if not Q is false, then let's see, then Q has to be true, right? It has to be true because of negation of this. Remember, we're looking for a row. So on this particular row, if there is one, then Q has to be true. And if it's true there, then it has to be true here too. Okay. So Q would have to be true. In this one, in the second premise, that has to be true. So P would have to be true and Q would have to be true, right? Because the second premise, we're assuming that it is true in order to find this invalid row. So if P is true and Q is true in a disjunction, well, we already know that's true because we have to assume it. So what this means is it's very possible that this row exists, or it does exist. It does exist as a possibility. So if you have a possibility where the premises are true and the conclusion is false, then you have an invalid argument. Okay. Now, I'm gonna end this one and start a new one for the next one because this is just way too long. Okay, let's see. Okay, I guess this is part 1 of part 2 of chapter 6. Okay, thanks and see you soon.